开始了吗？
Hello, how are you? Can you hear me? I have changed my computer and maybe we have problems with my audio. If anyone can hear me, can you write in the comments, in the chat? One moment. I have to check. Hello, anyone can say in the chat if you can hear me, if you can hear my audio? Okay, let's begin. We are going to review a little bit last day introduction to convolutional neural networks. We are going to finish the transfer learning approach. And after that, we are going to learn advanced application of convolutional neural networks, object tracking, object detection, segmentation, and really useful techniques. First of all, we are going to have a 5 or 10 minutes review. We see a lot of potential application. So last day, we talk about an image that is a matrix of pixels, and pixels are integer numbers between 0 and 255. When we have a color image, we have three matrices, RGB, one for red, one for green, and one for blue. If we have 1 million pixel color image, we are going to have three matrices if it's a square image of 1000 1000 pixels, 1 million pixels per one. We talked about that the dense layers has a lot of problems with processing image because they have a lot of weights, they tend to have a lot of overfitting, they are not catching spatial information because they are collapsing a matrix, a two-dimensional matrix, into a flat vector, a one-dimensional vector. Therefore, we don't have spatial information about the pixel surrounding other pixel. And we are learning with a dense layer, we are learning one distinct function for every different pixel. It's a lot of effort because we want a same function to translate over the whole image. This is because we start using a convolutional operation. We're going to have a window with some weights that we are going to translate it between all of the images, and we are making the same operation with the pixel of the window and summing them. This is much powerful than the matrix multiplication. This is convolution. In pure mathematics, we call cross-correlation, but in image processing, we call it convolution. In mathematics, convolution operation is different because it's commutative. But here we talk about this convolution operation. We saw some filters for example, for edge detection. And then we introduce the convolutional neural network. We are going to have layers of convolution. A convolution is going to have multiple filters. If we convolute one image with n filters, we are going to have n different matrices. We are going to say what is the number of filters and the size of the filter, the size of the matrix. We are going to use always 3x3 or 2x3 or 4x4. No different. We are going to have layers of convolution and layers of pooling. Pooling is an operation. We are going to have two different poolings, max pooling and average pooling. Max pooling, we are going to divide our image in matrix of the pool size, 2x2 or 3x3, and we are going to extract the maximum. Here, for example, in this window, the max is 6. Here is 8. Or with average pooling, we are going to have an average of all the pixels in the pool. In early 80s and in the 90s, people use average pooling, but in the 2000, people start using max pooling, and it's more powerful. You can try both, and you are going to see that max pooling has much best performance. Where in a convolutional neural network, we are going to have layers of convolution, pooling, convolution, pooling, convolution, pooling. We are going to have a lot. We are going to see now in transfer learning that we can have hundreds of layers. After all the convolution step, we are going to have a flattened step. We are going to convert a group of matrix into a flattened vector. We can use global average pooling, we can use flatten. We are going to convert this matrix, this tensor, in a flat vector. And after that, we are going to have a dense layer for the classifiers. Maybe we are going to finish in a softmax layers with the same number of neurons as the number of classes we have. If you have any question, you can interrupt me and ask. We see that in every layer, we are going to learn features, descriptor features that describe our problem. If we have a face recognition algorithm, in every convolution, we are going to extract higher level features. We talk about that augmentation is a really important step because most of the time we are going to have a small number of images. We are going to have a small data set. But if we are classifying, for example, lions, we are going to classify lions at night, at day, making a zoom, rotating the image. We are going to create a random transformation of our image for having a much more robust algorithm. We're going to rotate, flip, scale, reduce the quality of the image, compress it, decompress. And here we have the most important part of deep learning. This is the thing that makes popular deep learning, and we are using deep learning only because of that, because the transfer learning. We usually are going to have a project with very few photographs, very few images. And we know that with deep learning, we need very huge data sets. But we know, we talked about it last day, that we can use a pre-trained neural network as the base of our new neural network. We are very lucky because a lot of companies, for example, Meta, Google, Baidu, they train really big neural networks, with a lot of data set, with a lot of engineers working. They are very, very expensive. Maybe they cost dozens of $1 million, and they bring us for free. We can have a pre-trained neural network. For example, imagine that we need to distinguish to classify dogs and cats, and we have like a Google network that is trained in cities. We can detect a person, a car, a motorbike, a light, and we can use this network. We can bring it. We are going to cut in the flattened layer. We're going to cut. We are going to have only the pre-trained network, only the convolutional layers, and when we are going to introduce for example, our sigmoid with dog and a cat, or maybe a dense layer and our last layer. In transfer learning, we are going to frozen the weights of the pre-trained network. We are going to maintain always the same, and we are going to learn only the last layers that we have introduced. This is really, really powerful, and this works really good when we have very few images. We have another type of transfer learning that is called fine-tuning. It works really good when we have more images. Now we are going to use the pre-trained neural network and our introduce layers, and we are going to retrain the whole network. We are going to use the initial weights as the initial, but we are going to retrain all the network. And we are going to see it in, you have the link. We are going to review very quickly the implementation of the convolutional neural network. We use Keras. We can use any library, PyTorch or anyone. Remember that we download a flowers data set with tulips, sunflowers, dandelion, and daisy, and roses. Remember that we introduced the concept of data loading. The data loading is a way for dealing with really huge, really big data set. This data set is really, really small, but we are going to work usually with millions of images. This is because we are going to need we are going to use a more intelligent way than using a simple Python list, for example. We are going to use in Keras the dataset, object, but every library has its own data loading library. PyTorch has its one, Hugging Face had another one. It's going to generate like an intelligent Python list, a lazy one. We are going to deal with using of the graphic processing unit, the CPU. We are going to optimize all the data processing. We can store it in the RAM memory, and we can use prefetch. Prefetch is a way for optimizing our pipeline because we are going to can distribute our processing between the CPU and the GPU. We are going to use for example, the image augmentation or the image resizing in the CPU, in the processor, and we can change only the training epoch by epoch in the graphic processing unit. You can try to comment this line and compare times, and you are going to see that the training is slower, a lot of slower. Let's review how can we construct a convolution in Keras, a convolutional neural network. We are going to have our input layer. It's going to be the size of the image with the 3 channel because we have an RGB image. We are going to scale the pixel, normalize the pixel values. We have pixels between 0 and 255, and we're going to divide it by 255. And we are going to have our values inside 0 to 1 range. There are a lot of preprocessing, a lot of normalizations. Maybe you use minus 0.5 to 0.5. You can use a lot of different approaches. After the rescaling, we are going to have a convolutional layer. Here we are going to have 32 filters. This tree is the same as using 3 by 3. You can use the two ways. We are going to have a filter of 3 by 3 weights. Here, our filter is the 3 by 3. If we have 3 by 3 filter, we are going to have nine weights plus the bias. If we have 4 by 4, we are going to have 4 plus 4, 16, and it's a quadratic. If you increase the value, you are having quadratic increasing. After that, we are going to use max pooling. We can try parameters tuning to find a better architecture. You have to try, you have to familiarize, because it's a really hard problem to optimize the parameters. We can make a good search. You can use Keras tuner. Here you have a tuner for making an intelligent grid search. You can use a lot of different approaches. We're going to have convolution, pooling. We can add more convolution. We have to try different architectures. And after all of our convolution, we are going to have a flattened layer. We can also have a global average pooling. We can do both. It depends on the problem. Average pooling, global average pooling is in the last layer here to create the average of every matrix and have a vector of the average of the matrix. Sometimes it works better, sometimes it's not. After that, we have a dense layer. This is optional. And our output layer is going to be a softmax with the number of neurons similar to the number of classes we have. If we have a summary, we can see that most of the parameters are in the dense layers. It's happened a lot. The initial filters have very few elements compared to the dense layer. Here we have the training. Okay, and now we also talk about the data augmentation layer. We can have a random flip, rotation, contrast. If you search for Keras, here you have a lot of different ways of augmenting image. Share, sharpness, saturation, rotation. Okay, and now we are going to finish with the transfer learning practice. Is our 6th notebook. We are going to use Google Colab. We are going to use a graphic processing unit. In Edition, I have this in Spanish, but if you go to Edition, Notebook Settings, we can select for free a graphic processing unit. I'm going to execute all the cells. We import TensorFlow. We are going to download the same dataset. Maybe it needs a few seconds for downloading. We can also do it locally. I have in Colab and in my Visual Studio. You can use both. If you want to use local, you can download the Jupyter Notebook, or you can go to my GitHub and download the code or clone the repository. Okay, let's go to the transfer learning. We have the data set. We are going to create the data set, the data loading pipeline. I have set 96 by 96 of the resolution. This is very small, but this is only for being fast in the class. We are going to use normally 384 by 384. This is very standard. Or most of the networks are trained with these dimensions. We are going to see how we can make a transfer learning with PyTorch models, with Hugging Face models. We have a lot of different models. If we prefer to use Hugging Face, we can go to the Hugging Face page. We are using image classification, and we can select any of the network you prefer. You can use Hugging Face code, or you can also use a TensorFlow code. You decide. Here we are going to use models in the Keras model garden. We are going to use Keras applications. We search it in Google. I can include. We are going to have a table with a lot of different models. We have very old models. The first one, I think, the oldest one is that one. I think this is like 12 years ago model. It was very popular, but it's really old. We're going to have a lot of different models. We are going to have the size, the top 1 accuracy, the top 5 accuracy. Any one of you knows what's the difference between top 1 accuracy and top 5 accuracy? You can write it in the chat if you know. Okay, all of these models are training ImageNet. ImageNet is a really popular framework for benchmarking image classification dataset. We have like 20 million images training 1,000 classes. It's like a challenge, and every year you can see what are the best models. You can evaluate it. It has been a really powerful challenge that has evolved a lot the image classification step. And deep learning it begins to be very popular with this data set. You can see them here. I think you can see them. I think we have. Here you can see them. No, I cannot find, but you can search for the best models of the state-of-the-art models. They are all of them. They are training in this data set. This data set have 1,000 classes. For example, we have for a shark, we have a blue, white shark, a tiger shark, bull shark. We have a lot of shark. Maybe for the top one accuracy, we see if we have a white shark, it's only a correct classification if our class is a white shark. Top 5 accuracy, for example, we have a white shark, and the most probable class is tiger shark, and then the white shark. Top 5 accuracy is our true level of the correct classification is in the first 5 most probably probable classes. Therefore, the top 5 accuracy, it's very high, usually very high. We are going to have different size models. Here, the best one are I really use this one. This is really efficient. In my company, I use it a lot. For me, is the most efficient one. We have Comnex, and here we have the accuracy. We can see that these are the best models. And you have here the number of parameters. But maybe if you need a neural network for using it in real time, maybe you need a fast network. For example, this one is really powerful, but this is very big and it's very, very slow. Maybe you need a smaller one, but much faster. You have to decide. If you have a real-time problem, you have to select a smaller image. Here, now we are going to see how to use them. Now we have the data set. No, transfer learning. I'm going to, yes, here. For example, if we want, this is a very little one, only 14 megabytes. It has not a lot of accuracy, 70% of accuracy. That one has 80% of accuracy. How can we do if we want this? We select here, and we are going to collect this. We are going to copy this code. To copy this code, we come here. Here, we paste this code here, and we are going to only use these 3 parameters. We are going to use include top false because we are going to queue after the flatten. We are not going to use this part of the model because they have trained with 1,000 images. We don't want all his classes. We are going to use our classes. Input shape our image size. At the beginning, we are going to use transfer learning. With transfer learning, we remember that we are going to frozen the initial weights. If we use fine-tuning, we are not going to frozen it. But if we are going to frozen the initial weights, we are not letting it retrain. We have base model, trainable, a false. We are going to use, in the previous exercise, we normalize using a scaling of 1 divided by 255. We have a lot of different preprocessing. Here, we use the preprocess input, the mobile net. Every different net has its own preprocessing. How can we use it in a model? We are going to have a similar input layer. We are going to preprocess our input, rescaling, normalizing, and we are going to apply our base model to the preprocess. And after that, we can have a flattening, a global average pooling. We have to decide. We can add a dropout, we can add regularization. With transfer learning, you don't need it, but with fine tuning, yes. And we are going to use our classification last layer. We are going to have a softmax with 5 classes. And if we make a summary, we can see that this is the pre-processing step. We are not using any parameters because it's a scaling and dividing. Our mobile net, 2 million parameters, average pooling, and the last dense. 2 million parameters. Non-trainable parameters, 2 million. This is because we are using transfer learning. We are frozen these weights. And we are only going to train the last ones. And if we want to train the model, we can see that very, very, very quickly, we obtain really good validation accuracy. Last day, with a train convolution neural network, we only can approach like 65% of validation accuracy. We can see that maybe we can increase the number of epochs, but it's very flattened now. And we can see the prediction. Here he has predicted Daisy. Here we don't have errors. Maybe another one. You can see list. List. Skip the first one and see. We can see with another images. All are correct classified. Maybe here, for example, it has predicted this as a rose, but these are tulips. We have always, when we analyze the results of our algorithms, it's very, very important to see if we see patterns in our misclassified outputs. Here it was a rose, but he has predicted a daisy. Maybe we have to think maybe this is because we don't have a lot of, in the dataset, we don't have a lot of white roses. What can we do if we don't have a lot of white roses? We can do image augmentation, decoloring our dataset, because maybe it doesn't have to focus only in the color, maybe in the shapes of the image. We can do image augmentation, or we can collect more data. We can collect more white roses. Here the same. It's a tulips, and he has predicted roses. Maybe we don't have white tulips. I don't know. We have to see. It's very important to analyze our outputs. You can learn a lot changing and pre-processing and increasing the size of your dataset. Sometimes a lot of people that don't have experience invest a lot of time and money in fine-tuning your network, but it's a lot worth to modify your training dataset, increase the number of images, see in what classes are failing more. Maybe you have to collect more images. You have to do a lot of post-processing to your model. Maybe we have used a really, really small data network. Maybe we can train another one. We're going to train the one I like most, the efficient net. We are going to copy the code. You can see that we have used MobileNet V2 it only have 14 megabytes, 3 million parameters, and 70% of accuracy. That one has 6 times more parameters, a lot more accuracy, and a lot of more parameters. Let's try and see. We're going to see include top false. We don't want to use its input shape. Here. Boolean, we are going to use it after. We don't need classes because we are not using the top. We don't need this. And here we can see that we have the preprocessing step include. In the mobile net, we don't have it include. We download the model. It's bigger. It's going to last some seconds. We can see that this is, we can use summary. We can see that it has a lot of convolutional and Boolean layers. This is really deep network. Imagine to fine-tune all of these layers. We have seen that we have the preprocessing step included in our network. Therefore, we don't need to preprocess the image. Average pooling. And see that now we have 20 million parameters. Before we have 2 million parameters. Let's try it. It is gonna take like 1 minute because he has to transfer all the parameters to the graphic processing unit. And he has a lot of parameters. Maybe you have in your laptop a very small graphic processing unit. You are gonna have problems with your memory. It usually happens. Let's wait a little bit. We have to remember that we are using a free GPU that is not very powerful. If you pay Colab Pro, I used to pay it, but now no. If you can use Colab Pro, this is in euros, it's like $10 for having access to better graphic processing units. Here, the T4 GPU we can see is very old. Let's see. I don't. Let's see the characteristic of the NVIDIA T4 GPU. We can see that is 10 years ago. It's really old one. Maybe we cannot use it. Okay. We wait the results, and okay, we have it now. Maybe it's going to crash and we have to restart the kernel. Next day, I'm gonna use in my laptop because I have a better processor. Sorry about that. Maybe it's the total RAM of our. Maybe it's not the graphic processing unit. It's the processor. Okay, we will be back after. Other things that we can do. I do this a lot of times. We can combine a custom convolutional network with a pre-trained neural network. Why? Because maybe we are using a very different problem that the ImageNet dataset, and we can see, okay, I don't have enough image to make a fine tuning, but I don't see that the preload base model can find the features that describe our problem. I can say, okay, I'm going to use the pre-trained model, but I'm going to use in the other side also a custom convolutional neural network. Maybe I'm going to find a more advanced feature with this, and I'm going to create our network, the inputs, I'm going to pre-process. This is with the MobileNet V2X, and we're going to create two convolutional layers with 32 filters, 64 filters, and global average fullness. I'm going to have one branch, and the other one, I'm going to pass it to the base model, X and X, the preprocessing input going to the convolution and also to the pre-trained model. After that, we concatenate it. We collapse the two vectors into one, and we create a dense layer. We can see that we can have a better accuracy. And let's see if we have here, you have the efficient net. The first step was 5 minutes. We can see that we have very similar accuracy. Maybe we don't have enough image. We can see that the first epoch is much better, but we don't have a lot of difference. Let's analyze the results. We have similar validation accuracy with the efficient net, but that one, if you remember, I have a company for detecting skin cancer with hardware. I have a Chinese hardware, dermoscopy, and I use it. I have tried all the pre-trained models, the CompNext, visual language model, visual transformer, and that one for me is the most efficient when you don't have a lot of image. I have chosen this in a lot of projects, the EfficientNet V2. Here, that we can see that with the EfficientNet, that one is correctly classified, but that one no. Maybe it depends on the parameters and the architecture, but here maybe you need to increase your data set or modify your image augmentation pipeline. And if you want to use fine tuning, the only thing you have to do is set base model trainable true. We are going to have similar model, but it's going to last a lot more. You can use both of them. It depends in the number of images you have for training. Right. Okay, here, if you want to practice at home, you have here exercise with hints and you can complete it. I'm gonna finish the session. And let's start with the application of convolutional network. More advanced and more useful applications. If you have any question, you can ask me and you can interrupt the class. Let's see some convolutional neural network use cases, more advanced one, more state of the art. We are having now a really revolution in image processing, and we have a lot of different free algorithms and free models for productivizing them and extracting value. What we are going to use in most of the convolutional networks application. We can remember that we have convolution step, pooling convolution, then the fully connected layer, and then the softmax. We are going to extract our convolution map plus pooling layers for feature learning. It's going to be really powerful for extracting features that describe the image. We are going to use the last layer of our convolution for mostly every algorithm, for image classification, for object detection, for segmentation. We are going to use a lot. This is a really powerful step or extract feature for embedding one image into a vector. Let's see some advance. We just see multi-class classification. We have a convolutional neural network, and we finish in a softmax. A softmax is going to have discrete classes. We can have an image, and for every image, we are going to have only one possible class. Here's a dog, here's a cat. But what happens when we have a multi-level classification? In a softmax, we are going to have a distribution of our outputs, and we are going to have a frontier classification. To the left is going to be a dog, and to the right is going to be a cat. It's discrete. We can only have one per image, but we usually are going to have multiple objects in an image. It happens the same with processing, with natural language processing. If you have a news in the newspaper, it has a lot of classes. It can be sport, science, and you cannot have a softmax classifier, because softmax classifiers, it assumes that you only have one class for every item. Here you have multi-level. You can use a softmax, because what are you going to say? That 50% dog and 50% cat? Or imagine that you have two dogs. How you are going to deal it? You cannot use it. You cannot use a softmax layer. You have to use a different approach. Let's see the advance of the image classification. The one that we have used is the single classification, the simplest one. When you have only one object in your image, you can advance it with classification and localization. You can see, okay, here's a cat, but you need to determine where is the cat. You are going to draw a bounding box. You are going to have a lot of ways of processing the bounding box. We can see you can use this point and this point. You can use the middle point and the high and these two dimensions. You can use a lot of different techniques. Much more difficult problem is object when you have multiple objects. With you have multiple objects, you are going to use object detection. You are going to find where all the objects are, classify them. There's a dog, there's a cat, there's a duck, and you are going to use bounding box for everyone. And more difficult problem is instance segmentation. You are going to say, okay, here's a dog, but you are not going to use a bounding box. You are going to say that every pixel in the image that belongs to the dog. You are going to say every pixel that is a dog. Same with all of the objects. We have a lot of application. We can use face recognition. It's a really simple problem. Maybe 10 years ago it was much more difficult, but now everyone can create an image recognition pipeline. You can use in forestry to detect if you have helmet. You can use in fitness for counting the number of push-ups, or you can use it for counting people, see how many people are entering one shop, how many people are going out, how many people are buying in a shop, while looking for a different product. It has a lot of different applications. And nowadays it's really easy to use. Let's have a little introduction of how can we train a network for object localization. There are a lot of algorithms. We are going only to introduce it. We are going to use image classification with the location, with the bounding box. We have a lot of different ways of codify a bounding box. We can have for numbers, the coordinates of the middle point, the width, and the height. We can also hide the coordinates of this point and the coordinates of this point. There's a lot of ways of codifying it. We are going to have, as always, one convolutional neural network, but we are going to have 3 different outputs. One output is going to be a binary output that is going to be, is there an object? A sigmoid, because 0 if we don't have an object, and 1 if we have an object, because we can have an image without a car. We need to know if we have an object or not. After that, we are going to have the bounding box coordinates with the codification you choose with a ReLU, because they are all positive numbers. And after that, we are going to have our softmax, our classical output. It's going to be the classes we are detecting. And we are going to train a neural network with a combination of binary classification, binary loss, categorical cross entropy, binary cross entropy, categorical cross entropy, and maybe here mean square error. We are going to combine these. And this is a very powerful algorithm for object localization when you have only one object. But things are much more complicated when you have multiple objects. What can you do? Imagine we have to detect where we have a pre-trained network and we have to detect where is the car. We are going to use the first approach is, for example, create the sliding windows. You are going to execute your algorithm in every window. But maybe your car is very big and the window is very small. What can you do? You can increase the size of the window and detect where we have a car or where we don't have a car. And we can also increase the size of the window. What happens here? That by definition, executing a convolutional neural network is very time-consuming and very expensive. You are having a lot of operation, and you cannot use like 1,000 of time this convolution. This is why we discover an algorithm that is called. We have a lot of different algorithms. YOLO. You only look once. It's a really complex algorithm. We are not going to cover it, but we are going to use it like as an application. If you can see, this is like very similar to a convolution. We can codify this operation in a convolutional line. And this is how we are going to train a YOLO algorithm that we are going to see now, how we can use it in very easily with Python. We have a lot of algorithms, you only look once, single shot detection, region convolutional network, we have a lot of. But we are going to use YOLO because it's really efficient for production products. After that, how we can increase the difficulty? We are going to use semantic segmentation. We have an input image. We can use object detection to detect the card, but semantic segmentation is really different. Semantic segmentation is for all the image. Every pixel in the image is going to belong to one class. All the cars, maybe the road, building, you are going to separate all the images in classes. How do you do this? For example, with a car. We are going to have the image of a car, and you are going to have all the pixels, for example, 0 if there is no object, and you are going to use 1 for all the pixels of the car. You are going to predict this pixel map, binary map. You can resize it to reduce the size. You can do a lot of things. There are a lot of algorithms, ENAE, there are a lot. We are not going to cover it. And semantic segmentation is to say, okay, these all are people, same class, but instant segmentation is you have one people, different, to divide different objects. Let's see an algorithm that 3 years ago discovered Meta. It was really big and a powerful discovery. It has evolved a lot, but like 5 years ago, it was like a science fiction. It was really complex, and we can use now really good segmentation. We have much more powerful now, but I select this video because I think we can see really good the powerful tool. You can see that we can use a lot of things with this. We can select an image, a part of the image, and for example, we can use in online shopping. It's a really powerful algorithm, segment anything model. We have 3 versions. In Hugging Face, you have a lot of different models for image segmentation. We can go to task, computer vision, image segmentation. Here you have a lot. Depending what do you want. If you want to use SAM, you can. We have SAM 3 now. You have here the code, how to use it. But we are going to use another library that is called Ultralytics. We're going to see it now. There are a lot of different algorithms. Neural state transfer, I mentioned this in the slide. It was like 8 years ago. It was a really powerful technique that it was used, and it's a really good way to investigate how convolutional neural networks works, how the convolution layers works. It was really powerful, like 8 years ago, because you can combine a content image with a style image and modify an image. Now with generative models, with DeepSeek or ChatGPT, you can create this kind of image. But you have here how it works. We have a practice with this. You can go to my repository to this. All images are collected with Python and my notebook. You have this access to this. But now with generative model, it's easier. But it was a really powerful technique for investigating how convolutional neural network works. Another approach is face recognition. There are a lot of different ways. This is we can call it semi-super. maybe it's not self-supervised learning, but it's the beginning of this technique. What is, let's see before the difference between verification and recognition. Verification is a binary classification approach algorithm that is, you are going to have one image and you are going to say a binary decision, correct or wrong. Verification is with your mobile. It has to say if the image is for you or not. It's a simple approach, but you can have a recognition. Recognition is the classification. Like you say, okay, these people is not you, but it has its name. It's much harder. What's the problem with face recognition? It's what we call one-shot learning or few-shot learning. If we are creating, for example, in our building, an algorithm for verify if every people that are entering in our building is in our database, maybe we are going to send all to the building only one photo of us. We have to train a model to recognize one person given a single image. We have seen that for training a neural network, we need a lot of images. We cannot train a classifier. We have to use a different approach. We are going to use one thing that is called CMSNet. This is a really powerful algorithm. It's used a lot in natural language processing. We are going to have, as always, in every computer vision task, we are going to use always a pre-trained neural network. Here we are going to, it's called CMS because we are going to use same convolutional neural network to determine if these two people, Einstein, this is a famous Spanish scientific, old one, and we need to know if they are the same people or not. How are we going to use it? We are going to use two images. We are going to use the same convolutional neural network, and we are going to codify it in an embedding with a fixed dimension. We are going to call feature vector or embedding of our image. And if we have two vectors, how can we determine if they are for the same class, they are the same person? How can we compare two vectors? We are going to use the Euclidean distance. We are going to calculate the distance between the two vectors, the Euclidean vector, or we can also use the cosine distance, and we are going to have a value. And with that value, how can we determine if they are the same person or not? We are going to create a threshold. If the distance is less than a threshold, you can say, okay, these are the same people, and you can let them enter to your building. If they are above the threshold, you can say different people. But this is very beautiful, but we need a way for training this approach. There are a lot of things, semi-supervised learning. Here, we are going to use triplet lots. It's very easy one. You can use a lot of techniques nowadays. We have dozens of approaches. We're going to use here the triplet loss. We are going to have an anchor, an image. Positive is another photograph of another image of the same anchor class. They are the same people. And negative one is different one. We are going to go through the convolutional neural network. We are going to have two embeddings, and we are going to say, okay, what we need, what is our objective? Our objective is to say, okay, we need that the anchor is near to the positive. They have very low distance, but the anchor is very far away from the negative. We have to say that the distance between the actor and the positive is less than the distance between the anchor and the negative. Is less, and we are going to have here a threshold because we want to separate them as much as possible. We are going to say that the distance between the actor and positive minus the distance of the anchor to the negative, we plus the threshold, we need to maximize that. And this is how we are going to train our network. We are going to have triplets. And when we have trained like 2 or 3 epochs, we can select an anchor and positive. And with the pre-trained model, we are going to find for the nearest image, maybe his brother, that is not the same, but is the nearest. And we are going to try Obama, positive, and maybe his brother, and to try to separate them. This is a way for training a recognition or verification algorithm. We can use it a lot for handwriting signature, for recognize the boss, for text duplicates. We are going to use a lot of this in embeddings. This task is sentence similarity. You have in Hugging Face. You have a lot of models in text, natural language processing, sentence similarity. You are going to have here a lot of models. I think this is the University of Beijing. Let's see. Yes, Beijing Academy. This is sentence similarity. This is a kind of semi-supervised learning, self-supervised learning, and it's a very powerful approach for learning with unlabeled data. This is very important because with supervised learning, we need massive labeled data set. We need manual labeling. Is very limited because labeling data is very, 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 very expensive. We have in internet thousands of millions of images that are not labeled. With self-supervised learning, we can learn of data that is not labeled. With no manual annotation, it generalizes better. This is, for example, the retraining step for the large language model. Okay, now we are going to have a practice of object detection with Python. I think is better for using it. I think locally is better. You can use it also in Colab. You can use in Colab. You can go to the repository, or you can download the Python, the Jupyter notebook. You can download it. If you cannot download here, you can go to the repository, download all the code, or you can go to the notebook. We are going to use object detection with Ultralytics, and you can download here with this button. You can use both. I'm gonna use it in my local Visual Studio because maybe we are going to use the webcam. Let's introduce Ultralytics. First, we are going to go to the Ultralytics page. And documentation. I'm going to add the links. I'm going to write it here to write the links in the notebooks. Ultralytics is like a computer vision tool. It's an American company that develop YOLOS algorithms. They are really, really, really powerful and production ready. You are not going to find more efficient YOLO algorithms anywhere. I use it in my company for detecting for the melanoma, for detecting objects. Here you have the documentation. You have, for example, you have the models. You have here models, have YOLO models. They have, this is new. I think this is from this week. You have a lot of versions. You can see the timeline. And now they have the last generation of models. I think this is like 2 weeks ago only. You can go here. You are going to have a table, same as before with Keras application. You are going to have the size of the image, the precision, and the speed. If you have, this is nano, small, medium, large, or extra large. If you have a large algorithm, you are going to have a lot of more precision, but it's going to have to be a lot of slower. This is 10 times, 15 times slower. It has 2 millions flops operation of 55 millions. The nano YOLO models are really extremely powerful. I like them a lot. They are really, you can use them in the mobile. You can export, you can compress them, are really, really, really powerful. In this documentation, you have a lot of different, a lot of different models. Here are the models. You have YOLO, and you have different tasks. For example, you have segment anything model. Here you can call it with, this is a process with Ultralytics, and it's more efficient. It's a lot of, you can use it. You have code here, how to use it, Ultralytics. You have a lot of. You also have solutions that are key here. You can see they have changed the distribution of the weights, This, you have, for example, parking management. Here you have a video of how to, if you have a camera, to know where sites are empty. To say, okay, we have a free parking. And here you have a lot of similarity search. You can semantic image search for finding similar items. You have here a lot of tasks. You can use a lot of tasks here. Security alarm system. Maybe you can use, you have a lot of examples. Here you have the type of things Ultralytics can discover. You can use object detection, object segmentation, simple classification, pose estimation. Of vehicle, here you can have with different orientation, oriented object detection, and tracking with video. We're going to cover all of them. This is very powerful, and this is production ready. You can export to different. You can use it with RoboFlow. You can use it in JavaScript for use it in the mobile or in the navigator. You can use a lot of things. Here you can compress it to use it really, really efficient in a really efficient way. I think this is a really powerful. This is a really powerful library, Python library. I use it a lot. Let's introduce it. Is YOLO. Now, this year we have a YOLO 26. Let's see. If you are working locally, you have to install Ultralytics, OpenCV, and probably Torch. But Torch is installed with Ultralytics. You import Ultralytics YOLO. We're going to download. Let's execute every cell. We are going to download a group of images. Okay. First of all, we are going to start with this image for using the object detection. We have a lot of YOLO. Now we have to increase it with YOLO 26. And let's see how we can use it. It's very easy. You are going to select the model you want. Here you have YOLO 11th. 2 months, it was 2 months ago, it was the last one. But if we want to use this last one, this was like 15 days ago, it was the last one. YOLO 26, and we say what YOLO we want to use. YOLO Nano is the smallest one. Let's try it. I hope it works. I didn't try it before because it is new. No, it happens sometimes. Maybe we have to. Okay, I'm going to see it later. Maybe this is really new. Let's use YOLO 11. You have nano, small, medium, large, or extra large. How can we use the YOLO? First of all, we are going to load our image with OpenCV, and we are going to load our image in BGR. Remember, we saw last day that OpenCV works with BGR. It's the opposite of RGB. With RGB, you just work with this red, green, blue. We have this image, but what happens if you use BGR? It changes the colors. We have to be very careful with what we use. We know we can convert it. We can use convert to color with OpenCV, or we can only invert the last channel. We can do both. We have to be very careful because in OpenCV and in Ultralytics, we have to use BGR. We have to be very careful because if we don't use it, we are going to have a lot of errors. How can we do the object detection pipeline? We are going to have the image, but if we use the RGB, we are going to have problems. We have to remember that we have to pass the BGR. And then for plotting it, I have brought it here because you have to remember that we need the BGR image. You have to be very, very careful. What are we going to do? We have the YOLO model, and we are going to pass the image. And for example, let's analyze the result. We are going to have an object. It's going to be a list of objects because we can pass a lot of images. But if we only pass one image, we're going to go to the first one. We have a results object. This is very powerful. This is where we have all the information needed for drawing and all the information in the object detection. We have the original image, the name of the classes that we are training. This is a pre-trained model. This is a pre-trained model with the COCO dataset. We have 8 different classes. If we need a new classes, we have to retrain the model. We are not to have key points. This is post-estimation. We are going to see later. We are not going to have mask because this is not a segmentation. We have the original image, original shape, the speed, and the important thing is the boxes result. If we access to this argument, we are going to have all the object that has been detected with the classes. If you go with names, we can see we have detected the class 5, and we can see the class 5 is a bus. The 7 is a truck. And the 2 and 0 is a person, and 2 is a car. We have detected person, car, truck. We can see here. We have these classes detected with the confidence, 88%, the data, and the locations of the bounding boxes. Here are the location of all the objects detected. If we can return the annotated image with all the bounding boxes only with results.plot. Here we have the annotated image in BGR. We convert it to RGB, and here we have our object detection. We can see that here there are a lot of more objects. This is a really difficult image for object detection. Here you have the names, class 0 is person, traffic light, we have 80 classes. The detected classes, if we go to result.boxes, we have the confidence, the class ID, and the class name. We can access to the class name with class ID. We have one bus with confidence 0.92. This is all the detected elements. And a motorcycle with confidence 0.25. This is important because this is the lowest confidence. We're going to see later that we can lower this threshold. Here we have the bounding boxes with the coordinates of every image. We can use other tasks. Here. For example, you can use segmentation, you can use only classification, post-estimation, or oriented classification. Here, this is an introduction to the ultralytics object. Here we have a proper object detection recap. Can execute all of this. This is the similar code. Now we are going to inspect a little bit more only the detection step. After that, we are going to see the segmentation step. We have seen an introduction. Our dataset is trained with COCO. COCO is a similar to ImageNet, is a really useful dataset for learning object detection, object segmentation. We have 300,000 images. This is not a lot, but it's a really powerful dataset for training. You can download it, you can evaluate, can see everything. It's trained, you only have 18 classes to detect, as we see before. And here we have, remember, you have to use BGR, a dog and a cat. If we use the correct, we're going to have, I'm going to change it in the GitHub. This is a typo. I'm going to update it. You have much more. Remember that with RGB, you have 86 confidence. You have to use the BGR image. You can see that we can detect a lot of more objects and previous algorithm. Here we have here, for example, we are detecting all of the objects person. But we see before that we have a threshold for the confidence. We detect a lot of objects, but at first we are using that we only want to show the object that has higher than 0.25 confidence, but we can reduce this threshold. You can use, for example, how can we reduce it? How can we, yeah. Going to, for example, here you can see if we reduce the confidence, we are going to detect a lot of more objects, but we are going to have a lot of more errors. For a single motorcycle, we are going to detect like 5 or 10. We are going to see now how can we use to reduce this number of detection. Now we have the confidence, we can detect very low confidence. If we put confidence to 0.1, okay, it's a little bit better, but here we detect much more objects. Can reduce and we can increase. If we increase for 0.75, we're going to detect very small number of objects. Default, we are going to use 0.25. What is the intersection over union? Here we have the same. Let's change a little bit the numbers. And here, BGR. Here, intersection over union, we have to see, we have to see that when we load the confidence, we are going to, I'm going to zoom the image a little bit more. It's difficult to see here, but if you do it locally, you can see. For a single image, you detect a lot of different bounding boxes. But here we only have one motorcycle. Here we have a lot, and here we have a lot more. Here we can see that we have intersection over union 0.95, 0.75, and 0.05. What does that mean? Intersection over union, we are going to detect a lot of bounding boxes for an object, because here we have a car, here we have a car, here we have a car, but we have to collect all the different bounding boxes and return only one. How are we going to use it? With the intersection over union. If we have two different bounding boxes, the intersection over union is, if we have here two boxes, it's the area that we have with the union of the two boxes and the area they have in common. We can say if they have a little, if they are separate boxes, for example, this and this, the intersection over union is 0 because the area of intersection is 0. But if they are very near, the intersection is going to be this intersection divided by the union of the bounding boxes. And we are going to select a threshold to say, okay, these are the same bounding box or not. If we increase the threshold, very near bounding boxes, we are going to say, okay, they are different ones. And we are going to separate for one instance, we are going to detect a lot of different bounding boxes. But if we reduce the intersection over union threshold, we are going to collect all of them. This algorithm is non-max suppression. For example, we can see it here. If there is no overlap, intersection over union is 0. If they are moderate, here, for example, intersection over union is 0.2. If they have high overlap, here, because the formula is this intersection divide in the common, in the union, divide by the union. here you have an example of, for example, with this, we are combining these three bounding boxes in one. This is how it works internally, and these Ultralytics do this for you. The default values are intersection over unions 0.7 and confidence 0.25. You have to tune it. Maybe for your application you need different ones, or you need the same. Also, we can use, I have commented the code. We can try it. Maybe it doesn't work in you. I don't know what is the shortcut for comments. Okay. I don't know if it's going to work. It's a new laptop and maybe it's not going to work. Okay. Here you can use with your webcam and you can see that it's really efficient. This model is really, really efficient. You are using a lot of frames and really, really fast. We can try with a larger model, for example, with large one, this is heavier, and we are going to see that it's going to be very slow, because what we are doing here, we are using the webcam, we are capturing all the image. Here is okay. I'm going to access to the webcam of the computer, and I'm going to start cap.read. It's going to take a photo. Every photo here is in VGR. This photo is in VGR because it's OpenCV. I'm going to pass the frame to the model. We are going to make an inference. This is slow if we have a big model. We're going to have the results, result.plot, imshow, and we are going to here, person, I don't know, it's not very good. Tab, you can try it. Maybe in a Windows you have troubles with the webcam, I don't know. It's usual you have problems with the permissions and everything. Here you have exercise if you want to try it at home. Counting detection per classes. You had a lot of hints. It's really easy. Compare different models and count people. You can try it at home. And let's see the segmentation and post estimation. I'm going to execute all files. Okay. Here we have similar functions. We're going to use with OpenCV. We have a difference with object detection with instance segmentation. Image segmentation, it's much more complex. We are going to for every object, we are going to know which pixel becomes to the object. Instance segmentation, semantic segmentation labels every pixel in an image, but we cannot distinguish between different instances. We can have two classes, two cars, for example, but all cars is going to belong to the class car. But instance segmentation, we are going to separate different objects. We are going to have different cars. How can we use segmentation? It's really easy. Ultralytics, the power of Ultralytics is that it's really easy library and really efficient. You can use it in a mobile, in the navigator. We use segmentation model. We only have to use YOLO 11th line segmentation. And it downloads it, and you can use it. For example, how can we use it? This is a typo. I'm going to rewrite it. Remember that we have to go with BGR image. If you forget this, you're going to have problems. I'm going to change it in my repository. Here, if you execute your segmentation pipeline, you are going to detect all of the objects, but you are going to have the pixels that becomes to that object. Remember that we can reduce the confidence. We can detect more objects, or we can increase the confidence and detect less objects. And the confidence, the intersection over union. Here, we only have one bus. We can reduce the confidence, for example, here. And let's analyze the results object. Here, it's going to be similar as in the object detection, but here we are going to have the boxes that, remember, that is the object detection object. We are going to have here all the classes that we have discovered, car and truck or bus, the confidence, and the coordinates of the bounding boxes. But we have a different thing here that we didn't have before. Here, we are going to have the mask object. Before, if we only use object detection, if in the model we don't download it with this with check, if we only use YOLO 11th nano, we are not going to have the mask. But now we have the mask, and let's inspect how is it internally. We are going to have, for every object, we're going to have data, for example. We can see all we are going to have for every object detected a coordinate of, here I was looking for this, the coordinates of the pixels that belongs to that class. Here we have in boxes attribute, we have the number of classes detected, 9. the data shape and the detected object. And how can we extract the mask, the binary mask for every object? We have zeros and one if the car is in that pixel. How can we extract that binary mask? We are going to create here a extract segmentation map. We are going to have the detection result and what object we have to extract. The first one, the second one. What we are going to do? If we don't have detection mask, we are going to raise an error. We don't have any segmentation map. If you are trying to access to an index higher to the length of object detected, you are going to have an error. What we are going to use? We are going to have the height and the width, the dimension of the image. We are going to create a mask. We are going to create a zero matrix of the shape of the original image, and we are going to try to select ones to the pixels that belong to the object of this index, this index object, and zero the rest of the image. We are going to have the polygon that is going to be like the border of the object. You are not discovering all of the points. You have to draw it. You are going to have a polygon like here. You are going to have points here, 1, 2, 3, 4, 5 in the border. And with that border, you are going to use OpenCV for detecting the contours. Here, you are going to reshape it. And with OpenCV, you are going to fill the polygon. You are going to create the mask, and you are going to return the binary mask. For example, here, I'm going to execute this. Here, you can see that you have the original image. You can resize it. The binary mask are the binary points that belongs. And here you can have the binary mask and the image with the mask applied. What happens if we use our function? Similar. Here, we are going to have a matrix with false 0 is similar to false of the parts of the image that doesn't belongs to Einstein, and true the pixels of the image that belong to the people. How can we extract the segmentation map? We have the binary mask, the Einstein, the binary mask, and opposite of the binary mask. This is one where Einstein doesn't belong, and is the opposite. We have original image, binary mask, and the extracted object. How can we extract the object? We are going to copy the Einstein image. Here we are going to say, okay, in every point of the image that Einstein is not true, where is not Einstein, we are going to set background. We are going to draw it with a 0. We only are going to have the similar image in the points that Einstein belongs. We can do the opposite. We can create a zero matrix and write with the binary mask. You can use the same. Here you extract the object. Here you can do a similar thing. You can have the Einstein image, and you can set to red, for example. What happens if you set to red the points that we have binary max true? We delete Einstein. Now I think we're going to resolve it next day, because it is a little bit complex. Yes, we are going to solve next week because we don't have time enough now for for doing this exercise. But we are going to try to pixelate the people or blur the image of a person, and we are going to try to use the webcam next week to reload to capture the video, and you are going to or pixelate my face or pixelate the background. But let's do it next week because we need like 30 minutes more or less. And then we are going to use pose estimation. In pose estimation, we are going to have a similar approach. But our object result, we are going to YOLO 11 pose, not segmentation pose. Now, next week, we are going to inspect the results, but we are going to have the key points. We are going to explain it next week of the detection of the detected object, and which is going to be our result object. We are going to have all of the attributes, boxes, this is for the object detection, and key points. Key points, it's for the key points of an image. But we are going to go deeper next day. Okay. Next day, we are going to finish our computer vision with object tracking that it's very powerful, also with ultralytics. And we are going to use it with traffic image and also with a shop image for counting people that enters to a shop. And after that, we are going to learn about AI agents. That is a new framework that is very powerful and is the future and the present of everything. I think everything is going to have AI agents, and we are going to learn it next week and in 2 weeks. Okay, I think anyone have any question or any suggestion or maybe anything that they want to learn and I can create a practice for the next week, or any comments? Okay. I think we can finish and we can continue next week. Thank you very much and see you next week. If you need anything, you can write me by email or by the Moodle, and I can respond any question. Thank you very much and see you next week.